Aloha student, welcome back to Math 100. Today's topic is 13.2 Mathematical Expectations. Okay, so the first vocabulary we have here is called expected value. It's a new word, but the idea should be similar to weighted average if you had encountered weighted average before. Okay, so it's a type of average that some of you are familiar with. So expected value is a mathematical way and to use the probability, and probability we can say is the way, okay, and how much is the chance of that outcome happening, right? To determine what to expect in various experiments, right? Experiment is when you do activity and then you record the outcome, okay? So the expected value is more accurate the more times the experiment is run, right? So similar to the idea of the empirical probability gets closer to the theoretical probability when the more times the experiment is run, okay? So in the big scheme of things, this expected value is very similar to the notion of average, and to be specific, like I say, is weighted average, because the normal average is every outcome has equal chance of happening, equal probability of happening, but in the weighted average is each outcome is different probability of happening, okay? So a few good example or common example that this is used is the insurance company use this expected value method to calculate how much insurance to charge the policyholder. Okay, so that's using the insurance company a lot. And also in business, it is used in weighing the risk versus the benefit. Okay, so should I go into this business or not? Usually business do some analysis before they get into a new project. So this is expected value being used to calculate the risk versus the benefit. Okay, and number 3 way is to indicate a player. Like if you were to go to Las Vegas, what happened when the game is played repeatedly? Would you be making money if you keep playing the game, or would you be losing money? So that's another way for the normal people to use the expected value. Okay, if you are not in business, if you are not working for a company, that expected value can apply to you too if you are just going to Las Vegas. Okay, so the standard way to compute the expected value is to multiply the value of each possible outcome. Okay, so value means what? It's numerical. You can multiply if it's a word, right? If it's like head or tail, you can multiply head or tail. It had to be numerical in order to be multiplying. So it has to be a numerical value of the possible outcome by their probability of that outcome happening. Okay, so in a mathy language, we write it write the above words in expected value is equal to the first outcome, which is x1 numerical outcome again, times that probability of that outcome happening, and then the second numerical outcome, possible outcome, times its probability of happening, and keep adding it and add it all up, right? And so E of x is the expected value of the experiment, okay? And of course, it's on average after the experiment is run repeatedly. So the x1, x2, x2, xn are the possible numerical outcomes. Again, it had to be numbers before you can do the computation. And so the probability of the x1 is correspond to the value of x1, right? The probability of that first numerical outcome happening, and then this is probability of that second numerical outcome happening, etc. Right? So make sure you know what each notation means. Okay. So again, expected value, if you run it n repeated times, it's the n multiply the expected value of a single event. And I'm going to triple star here because this is a shortcut when things gets complicated when you multiply n by a single event. It simplifies things for the expected computation of the expected value, and we're going to see that in our example very soon, but we're going to come back to this summary statement after we see the pattern. Okay, so a good game, what is a good game? A good game is when the expected value is positive. Remember, expected value is the average of your value of your outcome. So it's not probability. So it can be positive or negative, right? So when it's positive means what? You are expected to make money. And then when it's negative means you are expected to lose money if you keep doing the experiment multiple times on average. Okay, one single time it's not indicative of the average, right? So the game is said to be fair if the expected value is 0, right? Like I say, when the expected value is positive, you are expected to make money. When the expected value is negative, you are expected to lose money. So when the expected value is 0, means nobody make money, nobody make lose money in the long run, right? On average, you remember the experiment had to be run many times in order for the expected value to be predictable in theoretical probability. Okay, so when the expected value is positive, the game is in your favor. And if the expected value is negative, then the game is not in your favor, right? Negative means you are expected to lose money. So when we say fair game, we mean nobody lose, nobody gain, so it's break even. Okay, so it's break even. So that's the definition of what a fair game is. Okay. All right, so it's very important that our x1 here had to be numerical, otherwise we cannot compute. Okay, so this first question here, it says what is the expected value of the number of heads, right? The number of heads. So when we are flipping a coin, you can expect to have head or tail, but this type of outcome cannot be computed, right? So instead of writing head or tail, we are counting the number of heads. So when it's a head, our x1 is how many head? 1 head, right? So when we have tail, then our the second value, right? Second possible outcome is 0 because its tail is 0 head, right? So we translate our outcome, if it's not numerical, we translate it into numerical outcomes by, you can count heads or you can count tail, but you have to give the definition. How do we translate it into a numerical outcome is we count the heads. So when it's a head, the sample space is a head or tail. So the head is 1 head and the tail is 0 head, right? Does that make sense? So that's how we translate it into numerical outcome. If it's not numerical outcome, that's why we can have the computation of the expected value. So again, expected value, this x here is a general x, right? It's not x1, x2, right? So it's a general x. So of all the x's that is, right? So your x1 is 1 head, right? 1 head. And what is your probability of having that 1 head? Because you flip the coin once, right? So if your probability of having that 1 head is 1/2, right? Half of the time you're going to get a head, and the probability of the tail, which is 0 head, is also half. And so if you 1 times 1/2 is 1/2, right? Multiplication first before addition. So anything times 0 is 0 in the second part, and so the expected value is going to be 1/2. Okay, so how can you get half a head? Okay, again, this is average, right? So this is average expected value of flipping a coin is you're going to get half a head. Okay, so it doesn't make sense how you're going to get half of head. Again, average, it can be fraction, it can be decimals, because we're running the experiment many times to get this expected value, right? So if you are flipping a coin once, it still follow the theoretical probability, okay? All right, so what is the expected value for the number of heads if you are flipping the coin 2 times, right? If you are flipping the coin 2 times your sample space, remember if you are flipping the coin 2 times, you cannot have head or tail. Is it head, head, right? Tail, tail, head, tail, or tail, head, right? So this is your sample space of flipping the coin. And how do we change this to numerical if we are counting the number of heads? This x1 here will be 2, right? 2 is what? The number of heads in this first outcome, and the second outcome, x2, is how many heads? If it's tail, tail is how many heads? Yes, 0 heads, right? And this x3 is what? That's also 1 head, right? As well as the x4, 1 head, right? So you can combine the x3 and x4 if you want, but it doesn't matter because they are all, have the same expected, the value of the outcome. So you can combine x3 or x4 and x4, or you can treat it as different, right? Counting number of heads. So your expected value of each one is going to be one way. If you don't combine the x3 and x4, it will be 2 times what? It will be equal, right? 1/4, because it's 1 out of the 4th, right? And then the second one, this is x1. Probability of head happening is 1 out of the 4, and the probability of 0 head happening is going to be 1/4 too, but the value of the x2 is 0, right? And then because the value x3 and x4 is the same, so you can combine that, or you can do it separately. You can do it like this: 1/4 plus 1. Again the x3, x4, 1/4. Right. So you can do it separately, or you can do it in 1. 1 times 2/4 is the same thing, right? So again, this is x2, and so when you take the average, it will be, what is it? 2/4 here, the first multiplication, right? And this is 0, and then this is 1/4, and then that's 1/4, and so together it's 1. Okay, so going back to this summary that I started here, we say the expected value, if you repeat it, it's going to be n. If you repeat it n times, in number 2, we repeat it twice. It says it's the one that the expected value of one single event times the number of times you repeat it. So does that work here? Number 2 is exactly 2 times, the repeated 2 times, so it's the expected value of this one single event times what? Times 2 to get to 1, right? So because we flip the coin 2 times, right? So does that work all the time? We can see it. Okay, this one works, right? That summary over there, yeah, we repeat it twice, so we take the expected value of one single event and times it by 2. That seemed to work for number 2. Okay, so what about number 3? Okay, what about number 3? We are flipping the coin, the same event, right? The same event, but it's repeated 3 times to become a compound event. So in number 3, we are repeating it 3 times. So if that theory works, right, we would take the expected value of that one single event and times it by what? Because it repeated 3 times, so it should be times it by 3. So if that theory works, we should be getting 3/2. So let's see if we are actually getting 3/2. Okay, so let's try. So expected value of the event, right? So make sure we know how many possible outcomes when we flip the coin 3 times, right? So if we flip the coin 3 times, we're going to get head, head, head. That's one possible. And tail, 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 one possible. Or what? Head, tail, tail, right? And head, well, tail, head, tail. And then tail, tail, head, and then head, head, tail, and then head, tail, head, and then tail, head, head, right? How many outcomes, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? And so if we are counting the number of heads here, the x1 here will be what? Will be 3, right? Because we're counting the number of heads, and the x2 here, counting the number of heads, will be 0, right? And this next 3, it's actually, we can combine it into 1 because it's all one head, right? It's all one head. If you want, you don't have to do so many. You can say the x3 is 1 head, right? And then the x4 here, this is all the same, all 2 heads, right? So x4 is also combined, right, with all the ones that's alike, right? So that's all 2 heads. So we have 4 possible outcomes. So the first one is x1 is what? 3 heads. The value, we are counting the number of heads, and how many out of the 8 do we have, right? How many in the 8 sample space do we have? We have 1 out of 8, so that's the probability. And then the next one is the x2, we have 0 heads, and how many out of that 8 choices we have in that sample space is what? 1 out of 8, we only have 1 of that, right? And then the next one, the x3 is what? 1 head. How many of that? How many of that 1 head, right? We have 1, 2, 3, right? You see that? 3, 8, right? And then the next one, the x4 is 2 heads. How many of that out of the 8? Right? You have 3 out of 8, right? You have 1, 2, 3, 3 out of 8, right? So that is our 4 possible kind of outcomes, counting the number of heads. And so again, this is x1, x2, x3. If we have same ones, we don't have to count separately, right? We can count it, the number of heads, if it's the same number of heads, you can kind of combine it. And so this first one, the first multiplication is 3 eighths. The second multiplication is going to be 0. And then plus the next one is going to be 3 eighths multiplication, right? 1 times anything is just original, right? So the 2 times 6 times 3 is 6, so that's 6 eighths, right? 2 times 3, right? 2 is 2 over 1, go to the numerator. And so when we put it all together in adding fractions, the denominator doesn't change. So 3 plus 3, 3 plus 3 plus 6, right? The 0 doesn't count. And so we have 12 over 8. And if we simplify, we divide it by what? Divide by 4, right? So then 12 divided by 4 will be 3, and 8 divided by 4 will be 2. And it exactly follow that summary that we put 3 star on, that you can just take the expected value of one single event and times the repeat, how many times do you repeat. So that's a shortcut. That's a shortcut that we can use if we find the pattern and we believe in it, right? We can use that as our shortcut. Does that make sense? Okay, hopefully you can change that to 1.5 too. Again, expected value is not probability, so it can go over 1, right? It can go over 1 if it's not probability. Okay, so that is the answer for number 3. Okay, hopefully that makes sense. Okay, and number 4. Okay, so what is the expected value of a single row of 6-sided die? Our sample space when we roll a die is what? 1, 2, 3, 4, 5, 6. So this one is different from the head and tail because the outcome is already in numbers, so I don't have to change the outcome because it's already in numerical. The other one, I had to change it in numerical by counting the number of heads, right? And so this one, I don't have to, and so it's slightly easier. And so my expected value, again, the x here without x1, x2 means the general x, okay, or average x. And the first possible outcome, because it's already in numerical, right? So I don't have to change it. So this is just x1, x2, x3, x4, and they're all different, so I can combine them, right? x5, x6, right? So they are all different. So one, you have how many probability of happening, 6 possible outcomes, or 1 out of 6 because it's only one single row, right? And add the 2, the second x2 with 1, 6, 3, 1, 6, 4 also have 1, 6, and 5 also has 1, 6, and 6 also have 1, 6, right? So if you kind of multiplication first, finish the 2 times 1, 6, 3 times 1, 6, 4 times 1, 6, 5 times 1, 6, and 6 times 1, 6 is 6 over 6 is 1, right? So you add the numerator together, 1 plus 2 plus 3 plus 4 plus 5 plus 6, I believe, is 21. You can double check, don't trust me. And so the numerator is 21 divided by 6. And so you can use it, reduce fractions, or you can make it into a decimal. So the expected value of a single row is going to be 3.5, right? 3.5. So on average, it's not going to be 1, it's not going to be on 2, right? So it's going to be 3.5. Okay? And again, this is not probability, that's why it can be bigger than 1. The expected value is not just probability, so it can be bigger than 1. Okay, so number 5, if you rolled it 2 times, right? If you rolled it 2 times, and our sample space, if you rolled it 2 times, it's going to be like 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. The first one is 1, right? 1, 6, 1, no 1, 7, no 1, 7. So it will be 2, 1, and then 2, 2. If I keep going, I'm going to get what? How many of that? Each one, first one is 6, second one is 6. So I'm going to get 36 of them if I keep going like this, 6, 6, like that, right? So that is going to take a while, right? That's going to take a while. And then this one, the average is what? The x1 will be 2, and this, because you add 1 plus 1, and this x2 is going to be 3, and your x3 is going to be 4. You're going to take the, average, right, of the outcomes. And so that's going to be taking a long time, right? So because it's 1 and 4, so it's going to be x4 is going to be 5. And if there's another 5, you can, combine them. But that is going to take a long time, so we're going to use our shortcut, right? So we're going to how do we use the shortcut? The expected value is, because we repeated 2 times, we're going to take 2, right, times the expected value of rolling it once, which is the result from number 4, and so we can just do 3.5, right? So the average is going to be 7, right? So it makes sense. The lowest one was 2, 3, 4, 5. I mean, this last one is going to be 12, right? When you add it up, so it's going to be 12. And so it sounds like 7 is somewhere in the middle, right? So that makes sense. Okay, so if you don't trust this pattern here, you can write it all out and take the average and see if the weighted average that is, to see if it is 7. So I'm going to trust the pattern and leave it there. Okay. All right, so number 6. Okay, I'm gonna box the answer for number 5. Number 6. It says many casino subscription service has a contest. Okay, so they're going to give you the price. I guess it's only one price because it's singular, and the company receive for that one prize, the company receive what 3 million entries, right? So what is the expected value of the contest in the nearest sense? Okay, so remember our x had to be numerical. So I'm going to make a table here. Our x's, again, the x is general x and then p of x, right? And what is the possible numerical outcome? What's the possible numerical outcome, right? So you either win or you don't win, right? So if you win, you're going to win how much? 150,000, right? If you win, that's if you win, right? Again, the x had to be numerical, 150,000. And what is the probability of winning? You're going to have only one winner, so it's 1 out of what? 3 million. 1 out of 3 million chance you're going to win, right? And what is another outcome? What is another outcome? If you don't win, right? And if you don't win, then your x is what? 0. It doesn't look like we have to pay, right? It doesn't look like we have to pay. And so you will have x that is 0. And what is the probability of that happening? Besides the winning one, everything else is everyone else besides that one person that wins. The other 2,990,000, I mean 2,999,999 people, the rest of it is not going to win, right? So that's out of the 3 million. That's the probability of not winning, right? So the probability of winning is 1 out of 3 million, and the probability of not winning is 2,999,999 out of 3 million. And the good news here is our expected value, even though it looks like a lot of numbers, is what? 150,000 times, right? This is the x1, right? Times the probability of 1 out of 3 million. And plus the second outcome, but because second outcome is 0, and so even though the probability is pretty complicated here, 2,999,999, it actually disappear all to be what? Anything times 0 is 0, right? And so we just have to worry about this 150,000 over the 3 million. And if you take out the calculator, 150,000 on the numerator and use division for your fraction, divided by 3 million is 60. And if you do that correctly, I think the answer is 0.05. And because our x is dollar sign, right? The unit for the winning is dollar sign, so this is 0.05 dollar, and all you can say is what? 5 cents. So the average winning, if that winning person were to share with the 3 million people that submit the entry, everyone will get 5 cents, right? So that's what it means by average, right? The average winning is 5 cents. Does that make sense? Okay, so sometimes it's good to kind of set up the table. What is your x, right? And again, x has to be numerical, otherwise we cannot do the computation. Okay, so hope that makes sense. And I love that 0, 0 times anything is 0. That's very wonderful, right? Less computation to do if you had that 0 there. Okay. All right, so for number 7, this is a automobile insurance company, like your auto insurance, has determined the probability of various claim amount for the driver between 16 to 21, right? So I guess the probability of the teenager or, the 16 to 21, their accident is higher than, the regular other mature driver, right? So the expected value of the claim is the expected average claim amount. Okay, so what should the company charge per policy if they want to make it a fair game? Remember what a fair game is? Means they are not going to make money out of you. They're just going to charge you what it costs them, right, on average. So it says the company charge per policy. That's the second question here, right? So this is the first question is if they want to make it a fair game, and what if they want to make it, they want to make $50 per policy if they want to make money. So the first question is how much they should charge if they want to break even. The second question is how much they should charge if they want to make $50 per policy, right? So maybe we should calculate the expected value for how much it will cost them to, run the insurance company for the people between 16 to 21, right? So they already list down all the X's for us, right? So the probability of no claim, zero claim means no claim, right, is 70%, right? 0.7 is 70%. So 70% of the people between this age group, it's not making any claim. They don't get into car accident, right? And the 15% will claim 2,000 small accident, right? So 2,000, and again, this is dollar sign. So 2,000, 15% of the time of this group is going to get into small accident. And then they have the claim of 4,000. I think it's getting bigger accidents. That's going to be, 8,000. I mean, 8%, sorry, not 8,000, 8%. And then this is fairly big accident to claim 6,000. And that's 5% of the people in this group, right? And then again, this is what? X1, X2, X3, X4, X5, 8,000, and that's 1%, right? And then the last one, this is X5, right? The probability of X5, and plus what? 10,000 times 0.01, right? The one in the parentheses is the probability, right? The corresponding probability times probability of X2 times, right? So add it all up, that's the formula, right? Probability of X3 times the probability of X4 times the probability of X5, right? And X6 times the probability of X6, right? That's by formula, right? And so if you can take out your calculator, even, your graphing calculator, don't do the, I do my typing wrong all the time, right? So make sure you are inputting this into the calculator correctly or put it into the decimals, okay? So what is the average, right? So the average cost for them is 1,100. Okay, I think I did it right. 1,100. So if they want to break even, first part of the question, they should charge what? They should charge what they cost them, right? So they should charge the consumer if they want to break even. This expected value here is how much average claim is, right? So because that's what I did is, average the claim. So they should charge what? $1,100 per policy, because that's what average charge per policy is if they want to break even, right? And number two, if they want to make $50, then what should they do? If they want to make $50, they should charge $50 more than what it costs them, right? Which is the 1,100 plus the 50, right? So it will be $1,150 per policy because they wanted to make $50 per policy, right? So because again, this here, the 1,100 is the average claim, right? That's the average claim. If they want to break even, they should charge how much average claim is, right? That's breaking even. But if they wanted to make $50 per policy, they should add on top of the average claim, right? Does that make sense? So this is a two-part question in this number 7. Okay, so hopefully you get a little bit comfortable and maybe try out number 8. Okay, and the clue is make a table like number 7 of your different numerical outcome, right? So this is numerical already. So this is your x1, x2, x3, x4, x5. Okay, so see if we can try it and see maybe what else we need to do. Okay, pause the video, make the table, and then see how far you can get. Okay, so let's make sure we are not afraid to make mistakes here and stop the video now. Thank you. Okay, I hope you have a chance to make a table. Okay, so I kind of make all the possible outcome of $1, $5, $10, $20, and $100 bill without thinking about how much I had to pay for it, right? $20 to for the opportunity to reach my hand into the bag to draw into the box, right? So I'm not going to consider the $20 later in the first method. So if I reach out my hand into the box and get a $1 bill, what the probability of me getting that $1 bill is what? Because it's what possible 1, 2, 3, 4, 5. So each one, if it's one type of bill each, it will be 1/5, 1/5, 1/5, and 1/5, and 1/5, right? And so your average winning is going to be 1 times 1/5 plus 5 times 1/5. 5 times 1/5, and then 10 times 1/5, and 20 times 1/5, and then the last one is add the 100 times 1/5. And if I do it correctly in the decimals, the answer, well, I can times all of this whole number, the x's into the numerator because it's whole number, and so it's going to be 136 out of 5, and that's average of 27.50. So on average, I'm going to win 27.50. But how much do I have to pay, right? I have to pay this $20 to play, right? So my average winning without consider how much I pay for the game is 27.50, and so the net expected value is going to be what? 27.50. Take away the cost to play the game, so my net expected value is going to be 7.50, right? So 7.50 is positive. So what does that mean? I'm going to expect to win on average, right? So positive is good game, right? It's a good game. 7.50 on average. Negative is a bad game because that's on average I'm going to lose. Okay, so this is method number 1. Is you think about your cost later. Just think about what is the average winning first. Okay, so that way I think it's easier, but some people or some books use the second way. So what they do is your $1, you need to subtract the costs at the beginning. Your $1, so for this $1 person who got $1 actually lose 19. So if you consider the cost at the very beginning, this person who got the $1 bill actually lost 19, and the person who got the $5 bill actually lost 15, and the person who got the $10 bill actually lost $10 because paid $20 and only got $10 back, right? So lost $10. And the third one, that's $20, actually break even, right? Because you pay $20 to play the game and you grab a $20. And so this last one here is you pay $20 and you get $100 back, so your net is 80. So if you consider your net for your X's, right, your net earning, then you don't have to do it at the end, but then that's a lot more computation. The probability of X is still 1/5, 1/5, 1/5, 1/5, and 1/5. So if you calculate that way, your expected value in the second method will be what? Negative 19 times 1/5, and then plus negative 15 times 1/5, plus negative 10 times 1/5, and 0 times 1/5 is just 0, and the other one is positive now, right? Winning 80, net winning times 1/5. And so if you, the denominator is 5, so if you take the negative 19 minus 15 minus 10 plus 80, okay, what do you get? You get, this is 34, right? That's 34, 44, 44, 44 negative plus 80, what is that? That's 36, positive, right? 36 out of 5, right? So 36 out of 5, what is that? So I think I did a computational mistake in the first part, and I think that's actually good because you do it 2 methods and you compare answers. So even though you set it up, sometimes you compute it wrong, right? So if you do it a second method, you can kind of, oh, how come it's different? This one is actually positive 720. So I think this is 2 here. I made a boo-boo. This is 2 here. I just 136 out of 5 was correct, but I just made a boo-boo in the decimal place when I did the copying. So both way, it should net 720, right? So the difference is consider your cost at the beginning, and you know, one is considered later, one is considered at the beginning. Either way you set up, then your answer is going to be the same. Your net expected value is going to be 720. Okay, 720. So this one on the left is to consider your cost later, and this one on the right is to consider your cost at the very beginning. So either way, you get the same net expected value. Okay, so I like the first way better because it's cleaner, but then don't forget to consider the cost at the end, right? So the downside is sometimes you forgot to consider the cost if you do it the more easy, clean way, you forgot the last step. Okay, so make sure you do that. All right, so let's try number 9 on your own, and then let's come back to it later. Okay. Okay, again, we're going to do this number 9 in 2 different methods, and then after that, you can choose whatever method you feel comfortable. And so this first method is we're going to consider the cost later. We're going to consider the cost later. Okay, so you pay $20,000. That's the cost, right? So we're going to consider that later. There's 2/3 of the probability you will graduate. And if you do graduate, you will make $1 million more in your lifetime than if you would have without graduating or without going to college. Okay? And so what is the expected value into the nearest dollar, right? So the cost again is minus 20,000, right, to go to the college. I think college is more than 20,000 now. This problem is probably old. Anyway, the first method, we're going to consider the cost later, right? So if you do graduate, you make more. This is if you do graduate, you make 1 million more. But if you don't graduate, then what? Because we are considering the cost later. If you don't graduate, then you just don't make, you make $0 more, right? It's not that you make $0, but you make $0 more than, you know, because you didn't have a graduate, you didn't have a college degree. So this expected value is how much more you will make with a college degree, right? So then that will be what? 1 million, right? The x1 times the probability of the x1, which is 2/3. And then again, 0 times 1/3 is just 0, right? And so that is the expected value of how much more you will make if you even attempt college, right? So 666,666, and to the nearest cents will be 67. But this is not considering, this is average how much more you will make, but you need to minus the cost, right? So because we're going to consider the cost later. The danger of this one is people forget to consider the cost, right? So the net expected value with the cost, right? It's going to be taking this number and subtract the cost, which is 20,000, right? So that is going to be 646,000, 666.67, because you minus the 20,000 on the cost, right? So that's your net expected value. Okay, so that's to consider the cost later. After you get the expected value, then you consider the cost. But you can also consider the cost earlier. So you will take the x, the original x, the 1 million times the cost at the beginning on your x's, right? And so this will be 20,000. That's the cost, right? So you consider the cost in both x's, your original x's, and the probability is going to be the same. Okay, so if you calculate the cost into the x's first, then we get the first x to be 980,000 times 2/3, and then minus or plus the negative to 20,000, right? Or you can minus times 1/3, right? So then if you do that with your calculator, you will get the same number, positive 646,666.67. Okay, so one way is to do the cost later, and one way is to do the cost earlier. So some people prefer the first method, some people prefer the second method. Some books use the first method, some books use the second method. It's the same answer, just a matter of which method you like better, so you can choose. Okay, does that make sense? Okay, so again, you can consider the cost earlier, consider the cost later. It's up to you, whichever way you feel more comfortable. Okay. All right, so number 10. Number 10, it says we are playing a game that using one die, and the player pay 3. What is the 3? Again, that's a cost, so it's up to you if you want to consider it earlier or later. Okay, and earn whatever number of player roll in dollars. So if you roll 1, you win 1. you earn 1, and if you roll 2, then you win 2. If you roll 3, then you win 3. Okay, so it says, is this a good game to play? Good game to play means what? The expected value is positive. Okay, so then it asks you what is the expected value to the nearest cents. Okay, and because we did that before, I think from number 2, right? We rolled a die before from number 2, and we say the expected value was 350, and because we didn't put the dollar sign at that time, because we didn't say if you roll 1 you win $1, if you roll 2 you win $2. But if you go back to number 2, our expected value is 3.5, and so we just put a dollar sign because that's what this one says, to win $1. You roll $1, you win $1. Right? But again, the way that we were doing in number 2, we didn't take into the consideration of this $3 cost. So we want to make sure we remember to, if it didn't calculate the cost, right? So remember to calculate the cost at the end, right? Because number 2 didn't calculate the cost, and so cost is what? $3, and that's minus, right? So you take your net expected value is what? Your 350. That is without considering the cost. Now if I subtract the cost, then my net, it's going to be what? Positive or negative? It's going to be positive 50 cents, right? Or 0.50, right? But it's still positive, right? So it's still positive, so it is a good game. So this answer here is actually answer to the second question, and the first question is a good game because you are on average winning 50 cents. Okay, so it is a good game to play. Does that make sense? Okay, so this is because we are borrowing from the result from number 2, so number 2 didn't calculate the cost, and so that's why we need to remember to calculate the cost at the end. We can calculate the cost at the beginning, but then we will have to do the expected value all over. But if I want to borrow from number 2, number 2 didn't calculate the cost at the beginning. Okay, so number 11, a game is played involving drawing a single card from a deck of 52 cards. If an ace is drawn, you will get 50 cents. If a face card is drawn, then you get 30 cents. If 5 of diamond is drawn, then you get $1, and the cost is 25 cents. So what is the expected value, the net expected value? Okay, so I think I'm just going to do the cost later. You can try to do the cost at the beginning. I'm going to choose the method to calculate the cost later. Okay, and so I'm going to ignore the 25 cents at the beginning. So I am going to list down all my x's, right? So my x's without considering the 25 cents of the cost is, if I draw an ace, I'm going to put 0.50 for 50 cents, and then 30 cents is 0.30, and then $1 is just 1, right? So this is all like in dollar, right? So this is 3 possible outcomes, right, without considering the cost, and I have to remember to consider the cost later. Right, so because I'm only drawing a single card, so it's not very complicated. I have 52 cards, right? And so in the 52 cards, how many aces are there? Ace is like number 1, right? So you have ace of diamond, ace of heart, ace of cup, ace of spades. So I have 4 aces, right? And so my probability of the aces will be what? 4 out of the 52, right? Because it's only single event drawing only 1 single card, right? And how many faces are there, right? You have the king, the queen, and the jack in each suit, right? So 12 face cards, right? 12 face cards. And so that's 12 out of 52 for the 30 cents. Less reward when you have more probability of getting it, right? So 5 of diamond, how many 5 of diamonds are there? How many 5 of diamonds, right? There's only 1, right? So 5 of diamond. Right, so that's why the price is higher, because you have less. So 1 out of 52. And so if you again, this first expected value is not considering the cost, so it's 0.50 times 4 out of 52 plus 0.30 times 12 out of 52 and plus 1 times 1 out of 52, and I think we're going to use the calculator to do the work for us, and average to be 0.13. And remember, this is without considering the cost, right? So how do we consider the cost, right? So we can consider the cost at the end. So we will take the net expected value will be the average earning, which is positive, right? This is average earning is what? 0.13, and the cost is subtract. The cost is subtract, right? 0.25, 25 cents is 0.25, and so that comes out to be what? Negative 0.12, and this is in dollars. So in other words, you're going to on average what? Lose 12 cents on average. Okay, on average. Does that make sense? So I prefer this calculating the cost later seem to be a little less work. But again, which method you want to do, it's up to you. So the question, number 1, the expected value, the net expected value is negative 0.12. And is this a good game? No, it's not a good game. Why is that? Because the net is negative, right? The expected value is negative, so not a good game. I'm losing money, right? So make sure you answer all the questions, not a good game, okay? And that's it for the expected value section. If you have any question, please reach out. I will be here standing by. Make an appointment using the office hour appointment tab. I wait to hear from you. And again, thank you for watching. Thank you. Bye.